Okay, so for the first one, the numbers, identify the prime numbers. So to recap, prime numbers, okay? Two factors. Okay, only two factors. They are 1 and itself. Only 1 and itself. So this limits us to only integers, only positive integers, which are greater than 1. The smallest prime number is 2. Example 2. Then the rest will be odd numbers. No other even number for prime numbers. Okay, so 2, 3, 5, 7. Instead of 9, 9 has more than 2 factors. It has 3 as well. So there is 1, 3, and 9. So 9 is not a prime number. Then we move on to 11, 13, 17, so on and so forth. Okay, so definition, you have to know for prime numbers. And one of the most common mistakes is stating that 1 is a prime number. So just write down your notes on your paper. 1 is not a prime number. Okay, just to remind yourself. So irrational numbers. Irrational numbers are numbers that cannot be expressed as a fraction a over b. Alright, I'll just put it aside. Maybe let's start with the definition of rational. Rational numbers will be a over b, where a and b are integers and b is not equal to 0. So this is the definition of rational numbers. Can be written as a fraction a over b. A and b are integers, can be negative integer, but b cannot be equal to 0. So let's break this down. Let's talk about the first portion, the fraction. And a and b are integers. So giving you some examples, we have 3 over 5. So our a and our b, they are integers, 3 and 5. It could be negative integers, for example, negative 4 over 7. It could be negative 5 over 1, which effectively is equal to negative 5. So when you see a number like this, negative 5, it is a rational number because you can put it as over 1. So we can also have our negative numbers in the denominator. For example, 3 over negative 17. So that's also rational. These are all rational. They can be written as a over b. What about 5 over 0? Is 0 an integer? Omena, is 0 an integer? Yes, it is an integer. However, 5 over 0 gives us, it's undefined. It gives us a math error on our calculator. So this is not a rational number because it is undefined. And that is where we have our second condition over there. The denominator cannot be 0 because once it is 0, it is no longer a defined number. So then how can it be a rational or irrational number? Okay, then we have another case. Instead of these fractions like this, they give you square root of 16 over 5, for example. Is this rational? So you look at it. Well, I do have it in a fraction, a over b. B is definitely an integer. The denominator is 5, it's an integer. But what about the numerator? Square root 16. It is actually 4 over 5. So yes, this is also a rational number. So it can come in various forms. How about things like pi over 7? Now is this a rational number? Is this rational? Matthias, is this rational? No? Why not? Which part of the definition it doesn't satisfy? The pi. What about the pi? What about pi? Okay, so you can say pi is not an integer, right? Pi is not an integer. I need it to be either a negative or positive whole number or 0 for the numerator. But this is pi. It is not an integer. Okay, so this is not. Then how about 22/7? Is this a rational number? Ning-Huan, is this rational? No, huh? Which part of the definition doesn't satisfy? There are two parts, right? Yellow and purple. Does it satisfy the yellow? Stop whispering behind her. Does it satisfy the yellow? Yes, right? Does it satisfy the purple? Does it satisfy the purple? So purple says that B cannot be 0. Did we satisfy that? Yes, we did. So did we satisfy both parts of the definition? We did. So the conclusion is, this is rational. This is a rational number. So why is it that we are uncomfortable with this being rational? Because in primary school we learned that take pi to be equal to 22/7. That is where it is confusing. Primary school we say take pi to be equal to 22/7. And then in secondary school we are telling you, we are repeating to you, pi is not rational. Pi is not rational. In other words, pi is irrational. And then when we throw you this number, then you think, oh, this is pi. But actually it's not pi, it's just an estimation. Okay? So this is rational, huh? Now, how about pi over 2 pi? Is this rational? Harry, is this rational? Not rational, huh? Why not rational? Which part doesn't satisfy? The yellow condition or the purple condition? The yellow doesn't satisfy, is it? Any disagreements? Or do you all agree that it is irrational? All agree it's irrational? Irrational? Aiza? Don't seem to agree. Nah, your turn over already. Yes, Aiza, what do you think? Sorry? Okay, so what made you unsure? What made you suspicious or hesitant to agree? You agree, Hina? Risha? What about you? Do you agree? Okay, which part are you unsure about? Are you suspicious about something? Which part? Pi and 2 pi, so? Oh, you agree, Harry also? Is there anybody who disagrees besides Harry? You told him to answer, huh? Okay, what do you say? Can cancel the pi, is it? So we can simplify. If we cancel the pi, what are we going to end up with? So this is going to give us 1/2. Now, is this rational? Yeah, right? A over B, 1/2. So this is rational. So it is similar to this case, where we need to simplify in order to determine whether it is rational or not. Can? Okay, we've got a few more cases that I want to go through. How about 0.3? Is this rational number? Is this rational? It is recurring. Okay, so just to recap, this means 0.33333, so on and so forth, forever and ever. So question is this rational or irrational? Okay, who thinks that it's rational? Raise your hand. Rational. Okay, who thinks it is irrational? Raise your hand. Irrational. Cannot put as A over B, where A and B are integers. Okay, who is not sure? Raise your hand. Not sure? Not sure? Come on, sure got some. Surely there are some who are not sure. Be honest, raise your hand. Who is not sure? Raise up high, raise up high. Raise up high. Okay, besides Akila, anybody else? Anybody else? Then the rest all very sure that it is rational, is it? Okay, so for those who are shy to raise your hand if you're unsure, This is what I told you all before. Every time you see the dot on top, automatically it is rational. Automatically it can be expressed as a fraction a over b, where a and b are integers, b is not 0. Always. So what is the equivalent form of this? Okay, 0.3 recurring is actually 1 over 3. Okay, always it is the case. So if I give you weird numbers such as 0.218 and then I put a dot on top of the 8, is this rational? Yes, it is. Just because there's a dot on top, confirm rational already. Okay, how about if I have more than one dot, maybe 0.2510238, I put a dot over here, I put a dot over here. So this number means 0.2510. Okay, so we copy the first portion, then we repeat from 2 to 8. So this will be 238, 238, 238, so on and so forth. Okay, so that's what it means. And same thing, because there are dots on top, confirm rational number. They are rational numbers. Okay, so now let's take a look at some irrational numbers. Irrational numbers examples. Okay, example will be square root 2. Square root 2, if you key in your calculator, it is 1.14 blah blah blah, right? So square root 2, 1.414 2135, so on and so forth. You cannot write it as a fraction where you have a and b and there are integers and b is not equal to 0. The best you can do, right, is this, square root 2 over 1. But it doesn't satisfy. Your numerator is not an integer. It is still irrational. So these are irrational numbers. So likewise, we have square root of 7, cube root of 9, so on and so forth. And then you also have your square root, your pi's. Okay, so pi, or maybe pi square, 2 pi, pi plus 1, pi minus 2 over 5. All these, they are all irrational. Square root 2 over 3, all irrational. Okay? So back to the question. Irrational numbers, in this case, we've got our square root 2 and pi, based on the list. So all the numbers with the dots on top, they are all rational. And then finally, we have our perfect squares. So perfect squares will be our example. 1, 4, 9, 16, 25, so on and so forth. So in the same way, you should be able to identify perfect cubes. Perfect cubes. So let's move on to the next one. Factors and multiples. Okay. So the number 324 written as a product of its prime factors. So they gave you a demonstration. 2 squared times 3 to the power of 4. So then express 168 as a product of its prime factors. So 168, you should be able to generate this. So what I like to do is 168 divided by 2. So 84, 2 again, 42, 2 again, 21, 3, and 7. So our 168 is broken down into 2 to the power of 3, because it appeared 3 times 3 times 7. Okay, so to complete this, 7 and 1. So we've broken down to our prime factors. And then the next part, explain why 324 is a perfect square. Okay, look at the question carefully. Using prime factors, explain why 324 is a perfect square. Are you allowed to say, oh, with my calculator, when I press square root 324, I get 18, therefore it is a perfect square? Are you allowed to say that? Cannot. They stated very clearly, use prime factors to explain. Even if they did not state that, using prime factors, if they just ask you to explain why 324 is a perfect square, you also cannot use your calculator. Okay, the only way that we accept it will be by talking about the powers of prime factors. Okay, now look exactly at what you wrote in your answer. Did you write something about the powers? Did you talk about powers? Is that a keyword, power? Should have, So once you have that keyword power, then you have to answer the next question. Power of what? What do you write? The powers of what? Or do you say the powers are all even numbers? Then I'm not going to agree with you. Powers of something. Powers of the prime factors. Do you have that? If you don't have that, write it down now. Powers of prime factors. Okay, so you are talking about the powers of the prime factors. What about them? They have to be multiples of 2. In this case, you can also state that they are even numbers. Okay, for perfect squares, you can either use multiples of 2 for the power, or you can say that they are even. The powers of the prime factors are even. We allow. The powers of the prime factors are multiples of 2. We allow. Okay, I'm not going to go into detail why they have to be multiples of 2. But that's for perfect square. What if the question asks for perfect cube? Okay, so back to the rough working at the side. If the question asks for prove that 2 to the power of 6 times 5 to the power of 12 is a perfect cube. If this is the question, you have to say the powers of the prime factors are odd. Is it odd? Oh, 6 and 12. Never mind, let's change it. Obviously, they are even over here. Let's change it to 9 and 15. Okay, so now the powers are odd. Does it mean that this is a perfect cube because the powers of the prime factors are odd? Because the previous case we said even, right? Besides multiples of 2, we said it could be even. So how about this? Perfect cube, therefore odd means perfect cube. So no, it doesn't mean that way. It doesn't mean that. It is not because they're odd, then they are perfect cubes. It is because the prime factors are multiples of 3. You can break them into 3 groups. And that is our basis for saying that it is a perfect cube. You can split all the prime factors into 3 equal groups. And for that to happen, we have to have the powers of the prime factors to be multiples of 3. So if I were to change the 15 over here to example 6, 6 is still a multiple of 3. So yes, this is still a perfect cube. Although it is made of 1 odd and 1 even power. Then in the same way, you should be able to explain why a certain number is not a perfect square. Okay, so prove that this is not a perfect square. Okay, or rather explain why. Explain why this is not a perfect square. So we say the powers of the so you say you just need to edit this. Not all powers of the prime factors, not all of them are multiples of 2. Not all are multiples of 2. That's why it is not a perfect square. Where? This one? This is not a multiple of 2. Okay, so next one. Part C. Find the smallest positive integer n for which 168 is a multiple of 3 to 4. Okay, so for this type of question, I'll put a star, very popular again. You have seen it multiple times. And if you have not learned the technique of answering it yet, maybe it is really time to do it. Because the fact that you have seen it appear so many times, it means that it is important for you to know how to do that. Which means that they might test you again. Okay, so for this type of question, sorry, not part B, part C. 168n is a multiple of 3 to 4. So you find the LCM of 168 and 3 to 4. And finding the LCM entails you just copying down all the prime factors, and then you take the highest power for every single prime factor for both 168 and 3 to 4. Okay, so once you have the LCM, this is the LCM, and this in your mind, you tell yourself that this is equal to 168n. There is a reason for us to generate the LCM of these two numbers. 2 power 3, 3 power 4 times 7. This is our 168n. Then you compare it with our 168. 168 earlier we found that 168 2 to the power 3 times 3 times 7. Compare these two. What's the difference? We've got 2 power 3, same. Oh, it is missing. There's a difference of 3 to the power 3. And yeah, that's all. The only difference between them, the differences between them is this part, 3 to the power 3. And that is our value of n. Because if you were to multiply 3 to the power 3 over here, then you also need to multiply 3 to the power 3 on the left hand side. And once you have done that, the center, they are the same. And that implies that this has to be equal to 168n. And therefore n is 3 to the power 3. So in summary, if this confuses you, for this particular type of question, all you need to do is find LCM of the two numbers. Just remove, they wanted 168n, just remove the n, ignore the n first. Find the LCM. Once you have it, compare it with our 168, the difference is just your n value. And then for part D, find the smallest integer k such that 168k is a perfect square. Okay, again, this is also very important. 168k is a perfect square. Let us write down again what 168 is. 2 to the power 3 times 3 times 7. They want 168k to be a perfect square. Let's ask ourselves, is 168 a perfect square? Is 168 a perfect square? No, it is not. Now let's check whether you know how to explain why. Okay, Zhen Jie, is 168 a perfect square? No. Okay, explain why. Using the explanation that we went through just now. The power of what? Sorry? What did you say just now? The powers of something, right? Powers of what? Why are you looking around? Powers of what? Okay, in your own words, try and tell me. Yes, powers of the prime factors. Okay, what about them? The powers of the prime factors are not multiples of 2. So this is not a perfect square yet. Then they tell us that, the question is not 168, it's 168k. So our intention is to multiply a k to the 168. Likewise, on the right hand side, we also must multiply by k. And they are telling us now that this is a perfect square. If this is a perfect square, then this must also be a perfect square. If this is a perfect square, all the powers of the prime factors must be multiples of 2. Let's take a look again at the prime factors, starting with prime factor of 2. Prime factor 2 has power 3. That is not a multiple of 2. So, this k over here that is introduced actually managed to change the power from 3 to an even number, to a multiple of 2. Because we are multiplying, the power will now go up. Okay, because we are multiplying by another number, the power will have to go up. If we are dividing, the power will go down. Okay, so now we are multiplying inside this k. Definitely, there is a factor 2 inside. Only then can I change the power for 2. And within the k, how many 2's would there be? It could be 1, it could be 3, it could be 5, 7, so on and so forth. That will ensure that the new power of 2 becomes a multiple of 2. Okay? Because if k has 1, 2, just one of it, the power will be now 4. If there are 3 2's, then the power will become 6, which is still even, so on and so forth. Hey, but we cannot accept so many answers. So if you look at the question again, it says the smallest the smallest integer k. Smallest. Therefore, we are only taking 1, 2 to be inside the k. There is only one of it. So k will be equal to 2 to the power of 1. Such that when you take 2 power 3 times 2, you get 2 power 4. Now it's a perfect square because the power is multiple of 2. Then let's take a look at the next prime factor of 3. 3 has the power of 1. It is not a perfect square yet. Inside this k, there has to be another 3. It could be 3 to the power 1. It could be 3 to the power 3, 3 to the power 5, 3 to the power 7, so on and so forth, such that when it is multiplied to another 3, the final power of 3 becomes even. But the question says they want the smallest k. So we have to choose the smallest option, which is just one of the 3. And likewise, we do the same for the 7. Multiply by 7. And now, my 168k becomes 2 to the power of 4 times 3 to the power of 2 times 7 to the power of 2. Now it is a perfect square, and this is the smallest perfect square that is possible. And the k value will be 2 times 3 times 7. So 6 times 7 is 42. This is the answer for k. 42. Look, find the smallest integer k. They did not say leave in index notation. So you have to evaluate it to become 42. If they say leave in index notation, then you leave it as 2 times 3 times 7. Okay, now using the same question, I'm going to form a new question. 168 over k is perfect square. Okay, 168 over k is a perfect square. So what is the value of k? So find k. Very similar approach. We write down 168, 2 to the power of 3 times 3 times 7. This is our 168. Divided by a certain number, k, will result in a perfect square. What should the perfect square look like? Currently, this is not a perfect square for the same reason that Zheng Jie mentioned. The powers of 2, 3, and 7, they are not multiples of 2. But the moment if I divide it by a certain denominator, and I tell you that it is a perfect square, we can now identify that the result has to be 2 to the power of 2. The power has to go down because we are dividing by number. You cannot increase the power to become 4. It has to go down to power 2. Okay? Which tells me that in my denominator there must be a 2. Just one 2. So that 2 power 3 divided by 2 gives you 2 power 2. But then what about a 3 and a 7? They are currently powers of 1 and power 1. The final answer is a perfect square. So from 3 power 1, what should I change it to become? I cannot make it 3 power, I cannot leave it as 3 power 1. I cannot have it as 3 power 2. Cannot. 3 power 2. Although the right hand side 3 power 2 is a perfect square, but the power actually increased from 1 to become 2. Cannot happen because we are dividing. 3 divided by integer cannot result in 9. 3 divided by integer cannot result in 9. So, the only option we have left is to put a 3 in the denominator. And then, it disappears. No more 3. And the same thing for the 7, multiply by 7, it disappears. So the answer is 2 square. I mean the perfect square is actually 2 square. And the value for k is 2 times 3 times 7. Alright? Oh, and this value is actually 42. What do you notice about these two answers? They are the same. 42 and 42. Whenever we are dividing or multiplying by k, okay, whether you divide by k or multiply by k, for a perfect square, your answer is the same. Only for perfect square. Because whether you increase the power by 1 or you decrease the power by 1, in both instances, you get the same value of k. Because after every odd number is an even number. Before every odd number is an even number. That's the logic behind why the answers are the same. Now, if the question is asking about perfect cubes, then the answers will be different already. So back to this. To make this a perfect cube, what was the other number? 3 and 7. 3 and 7. To make this a perfect cube, we have to think about what the perfect cube should look like. Okay, what do you think the perfect cube should be? This answer on the right hand side. A perfect cube has powers of multiples 3. Say again? No, that is the explanation why it is a perfect cube. But I want the right hand side to be a perfect cube. What would it be? It's like earlier on, right, when I say I want it to be a perfect square, then the right hand side will be 2 square lah. But then I had to reduce the powers by 1 for all of them. But now I want it to be a perfect cube. So what will the right hand side be? What do we expect it to become? What do you say? Increase the power to 3. Increase which power to 3? What do you say? Increase the power of 3 to become 3, is it? So are you saying that the answer is 3 to the power 3 times 7 power 3? What about the 2? Disappear, is it? Huh? Leave it. So you're saying that it should look like this, is it? Okay. If this is your objective, let me rewrite it. 3 power 3 times 7 power 3. If this is your objective, okay, what should I divide by in order to get this? What should I divide by? You know, you're partly correct. Yeah, this is a perfect cube. Good, perfect cube. Because all the powers of the prime factors, they are multiples of 3. Good. But what are you going to divide by? Shall we try? Okay, what would you like to divide by? I guide you through. Choose. Oh, 3, divide by 3. If we divide by 3, what do you think will happen, we think? What happened over here on the left hand side? Come on, primary school maths. If you divide by 3, what's going to happen? What's going to happen? Did he say something? What's going to happen, we think? 3 over 3. You want to come over here and whisper in my ear? Don't want, right? Come on. Did he say something? No? If Sean cannot hear you, I definitely cannot hear you. What's going to happen? Oh, they cancel each other. So any more 3 left? No more. Then how can the power become 3, right? So is it possible? Not possible. So like I mentioned, when we are dividing by something, the power actually goes down. From power 1, it can only go down to 0. Perhaps it can go down to -1, -2, -3, but that's not our objective. Okay? So what have you learned from this exercise, we think? Is this possible? Why not possible? Why is it impossible? I'm going to call somebody else and explain why this is impossible, so you better think about your answer. So yes, we think. Cannot be divided? What cannot be divided? What do you think? Do you truly believe that 3 power 3 is impossible now? Or you're not sure? Not sure? Okay. Fill in the blank. 2 over blank equals to 1. Okay, what's in the blank? What's in the blank, we think? 2, okay, correct. 2 over blank equals to 2. Okay, fill in the blank. Okay, very good. 2 over blank equals to 4. What's in the blank? Can this be done? Can this be done? Why cannot? Cannot. What's in the blank? 0.2. No, 2 divided by 0.2 is not 4. 0.5, okay, 0.5 is correct. Correct. Hey, 2 over x lah. 2 over x equals to 4, find x. So just change the x at the 4 position. So 2 over 4 equals to half. So x equals half, okay? Now, what do you notice in these 3 cases? On the right hand side, the numbers are smaller than or equal to the numerator. Smaller than or equal to. And that happens when the denominator is also smaller than or equal to the numerator. So the effect of dividing by a number that is smaller than or equal to the numerator will result in an answer that is smaller than the numerator. Okay, let me rephrase that. No. Okay, that's not right. In the denominator, if the denominator is greater than or equal to 1, yes, okay, so that's correct. When the denominator is greater than or equal to 1, the result is going to be smaller than or equal to the numerator. Because we are dividing a certain number of sweets by a certain number of people, which is more than or equal to 1, then everybody is going to get fewer sweets than the original total. But when we start to divide by a number that is smaller than 1, our final answer is going to be bigger. Because we are effectively multiplying. When you divide by half, it is actually multiplying by 2. When you divide by 1/3, you are multiplying by 3, so on and so forth. So, if we are focusing only on the 3 over here, 3 is a small number. And yet, 3 divided by an unknown results in a bigger number. That is only possible if we are dividing by a number that is smaller than 1, which is not what we are looking for. K is an integer. So we cannot have the denominator as less than 1. Our only options are the denominator has to be integers, more products of integers. And that is why when you decided to make 3 to the power of 3 as the result, there is no way you can put an integer. When you take 3, divide by another whole number, you cannot get 27. 3 to the power of 3 is 27. You cannot take 3 divided by any number that is an integer and you get a bigger number. When you take 3, you divide it by, let's say 3, you're going to end up as 1. You cannot get a higher power. The power has to go down. Can we think? Okay, so now we have established why it cannot be 3 to the power of 3 over here. So can it be 7 to the power of 3? Yixuan, why cannot? Please give me the correct answer. Why cannot be 7 power 3? Because 7 power 3 is bigger than 7. I cannot divide 7 by a whole number and result in a bigger number. So this is impossible. And therefore, the perfect cube is actually 2 to the power 3. And then for this to happen, the denominator has to be 3 times 7 by getting rid of the 3 and the 7. And therefore, the value of k in this case is 21 for it to be a perfect cube. Okay, so just remember the number 21 in your mind, 21 if you are dividing by k. Because I don't want to write so much already. Now I'm going to change this to become 168k. It's a perfect cube. Then what does it look like? Times k. So on the right hand side, it has to look like 2 to the power of 3 times 3 to the power of 3 times 7 to the power of 3. Increase all the powers to become multiples of 3. And therefore, k equals to 3 to the power of 2 times 7 to the power of 2, which is 9 times 49, which is definitely not 21. Okay? So when it is a perfect cube, whether you are multiplying or dividing by k, you will get different answers. But for perfect square, the answers they will be the same. Next one. At the bottom of the page, bulbs A, B, C start flashing together 8:45 every 20 minutes, bulb B 35, C every 90 minutes. What time do they flash again together? So we are trying to find the LCM. So put your working down neatly. One column for each prime factor. So in this case, I have this column for prime factor 2, another column for, oops, okay, I didn't follow my own advice. And then over here, in the middle will be my prime factor of 3. Okay, put them down in rows neatly. And when you have that, just copy down the prime factors 2. Okay, 2. Highest power is square. So put on the square. Then copy down the next one. Prime factor of 3. Highest power 2 again. Yes? Sorry? 21 hour. Oh wait, this is in minutes, is it? This is in minutes. So divided by 60, really? Wow, 21 hour, thank you very much. Okay, thanks Aloysius. Then back to this. Prime factor of 5, highest power is 1. Next, prime factor 7, highest power is 1 again. So we get 21 hours is the interval between all of them flashing at the same time. So if they had flashed together at 0845, the next flash will be 0845 plus 21 hours, and we get 29. 29, but we cannot have 29, right? So we need to take away 24, so it becomes 05 4, 5. Next day. Right? Okay, thanks for pointing out my error. So please write down next day over here. In the question, it might have included on Wednesday, 8:45 they flash. So the next time will be 5:45. I say Wednesday, right? So Thursday. Next page. Okay, cocoa, milk, other ingredients. So CMO over here. Ratio 4:3:5. So state clearly. Now they tell you that the mass of the chocolate 126 grams. So chocolate, total mass of the chocolate 126. So we've got a total of 12 units in total, representing 126 grams. They are asking us for the mass of the milk. So M, 3 units only, will represent your division. Then do your multiplication. 126 over 12 times 3, 11.5 grams. Then put on a statement. Okay, I didn't write it. Mass of milk. Yes. You mean I pressed wrong? Oh yes, 31.5. 31.5. Good job. 31.5 grams. Now you all know why on the first week of school, when you all return, I told you all that I finished this in 1 hour, right? There are a lot of mistakes. Let me find all the mistakes. Okay, part B. The chocolate sold in boxes, $9.60 at sale. So it's $72, bought as many. Okay, so just divide. He cannot buy 7.5 boxes, so he only bought 7 boxes. And then how much money was left? So half of the $9.60 will be $4.80 left. Okay, this part is just primary school maths. Okay, not gonna talk more about it. Next, speed. 50 kilometers per hour. So this is how we can rewrite our 50 kilometers per hour. Per refers to divide. So divided by 1 hour. Per 1 hour. 50 kilometers per 1 hour. Over 1 hour. So since they want it to be meters per second, change your numerator to meters, change your denominator to seconds, and get the answer. This is actually 13.88888 recurring. 8 recurring. So we want to write it as exact. That will result in a fraction. I am not going to accept 13.9 meters per second. No, not 13.9, because that is not accurate anymore. And then similarly for next one, 3.8 meters out of 1 second, 3.8 meters per second. Convert it to kilometers per hour. So in the numerator, you need to divide by 1000 to get from meters to kilometers. To get from second to hours, you need to divide by 3600. So I'll just work out the math, and you get 13.68 kilometers per hour. Exact. Okay, now B part 1. Average, he walks 1000 meters, so distance settled. Average speed 4 kilometers per hour. Then run 1.3 kilometers 5 minutes. Okay, time taken to walk the 1000 meters. So time, distance divided by speed. Got error again. Where the clock divide into 4 parts. So 1/4 will be 50. Yeah. Okay, you're confusing with 100 lah. Okay, so that's the 80. You said 25, right? You said 25 or 20? Okay. So anyway, this is one thing that okay. So 15 minutes over here, and then for part 2, his running speed in kilometers per hour. So 1.3 kilometers per 5 minutes. So you need to convert that to hours divided by 60 and you get 15.6 kilometers per hour. And finally, average speed for the whole distance. Average speed, put a star. Total distance divided by total time. What is the total distance traveled? We've got 1 kilometer plus 1.3 kilometers. This is our 1 km plus 1.3 km. Okay, then our total time. In the first part, it was 15 minutes. Then we had another 5 minutes. So 20 minutes out of 60 minutes. There's no rest time. Okay, so this is our 15 minute plus 5 minutes. And we get an average speed of 6.9 kilometers per hour. I emphasize again, average speed is not found. It is not found by first speed plus second speed divided by 2. No, And in addition, just put down notes. If he rested for X minute, then include X in total time. In this case, in this question, they did not tell you he rested, because that's the other thing we want to check whether you learned or not. Average speed will take into account the time that he is not moving. So if he rested for X minute, we must add in the X minutes for the total time taken. Next, percentage conversion. Okay, for A, in 2008, best time 9 minutes 30 seconds. 2009, best time 10% less than the time in 2008. You need to be able to identify which is the original. What are we comparing with? Okay, so there are 2 years over here, 2008 and 2009. Whichever that we are comparing with will be the original, will be the 100%. In the second sentence, his best time was 10% less than the time in 2008. So we are comparing with 2008. This portion, comparing with 2008. So when we compare with 2008, it means that 2008's time represent 100%. If 2008's time represent 100%, then 2009's time will represent 10% less, 90% of 2008's time. Alright? And that's how we ended up with 90%, which is 0.9. 90% is 0.9 times 9.5 minutes. We get 8.55 minutes, which is 8 minutes 33 seconds. Any issues? 8 minutes 33 seconds, Compare that with, and now I'm going to write the wrong answer. Compare that with, I'm going to write the wrong answer on the paper. %100% represent 2009 time. And then since it is 10% less, right? So 110% represent 2008's time. Okay, in red, it is wrong. Can you see that in both cases, there is a difference of 10%? Right, in the pencil, which is correct, 100%, 90%, difference 10%. But in red color, 110%, 110%, the difference also 10%. But the working is different. And in fact, this is entirely wrong. The reason this happened is because you did not know where our 100% belongs to. And then I reiterate, in order to decide where the 100% is, you have to identify what you are comparing with. If it is 10% less than the time in 2008, we are comparing 2008. Comparing with 2008 means 2008's time is the 100%. The working in red will be wrong. So let's move on to the next part. Part 2. In 2008, his time of 9:30, 9 minutes 30 seconds, this was 5% less than the best time in 2007. Okay, this time was 5% less than the time in 2007. This implies that we are comparing with 2007. We are comparing with 2007 in part 2. So now our 100% will represent time in 2007. Now it has changed. 100% represents the time in 2007. And if in 2008 this particular time was 5% less, then it gives us 95%. Will represent time in 2008. Now there's a change. Compare part 1 and part 2. 2008 time, 100%. 2008 time, 95%. It is the same time, but depending on how you phrase it, depending on what you are comparing with, the percentage representation will change. That is why in part 2, our answer is as such. You just divide by 0.95. Okay? If you work out, if you want to write everything out in the same format that I always use, then it will look like this. 95% represents 9.5 minutes. 100% represents, so 9.5 divided by 0.95, and you get 10 minutes. Oops. Okay, then next thing I want to highlight is I chose to write 9.5 minutes in my working. So my result will be 8.55 minutes for the part 1. I did not use 9 minutes and 30 seconds as given in the question. Because when it comes to pressing into your calculator, it is easier to work in decimal. After that, you do the conversion yourself. But if you want to work with minutes and seconds, you can go ahead. Just be very careful. And now part B. Original price, $96. Original price of painting, $96. In February, the price increased by 12%. So in February, the price is now 112% of the price in Jan. Then in March, the price decreased to 25% of the price in Feb. So now we're comparing to Feb. And it has dropped 25%. Then find the price in March. If you answer to the nearest end. Okay, so I just did everything in one single working. You can actually expand this and come up with more clarity, but I'll show you why this is quite easy to understand also. I am now going to translate all the words over there to our mathematics. They want the price in March, right? So the price in March. And I'm going to go backwards now. Find the price of the painting in March. So in March, the price decreased to 25%. Decreased to 25% means that the price is now 75%. 75% of the price in February. 75% of the price in Feb. So this is the price in February. Now in February, its price increased by 12%. Increased by 12% means 112%, 1.12. And that's where I get my 1.12. 1.12 of what? 1.12 of $96. So everything in one line. And let me check my calculation. 0.75 times 1.12 times 96. And we get $80.64. That's the price in March. Ken? Any questions? Any questions? I'm very nervous now. A lot of conversion over there. Are you talking about this question or next one? Next one, huh? This one. Okay, so any questions for this? Any alternative solution that you want me to check for you? Anything you want me to check for you? Okay, pause. Nearest end. Huh? Correct. Okay, so where's the confusion? Nearest end, no? 6-4. Huh? Okay, so wait, is this because you all grew up in an era where there is no 1 cent, 2 cent, 3 cent, 4 cent? The only cent you all know is 5 cent and 10 cent, 20 cent? Okay, so when we talk about nearest cent, it can go down to 1 cent, 2 cent, 3 cent, 4 cent, 5 cent, 6, 7, 8, 9, 10 cents. Okay? So 2 DP. That's why we always say 2 DP lah. Have you all seen the 1 cent coin before? Never. Okay, so I don't know when, but the 1 cent coin was phased out in Singapore. In the past, right, we had this copper-ish color 1 cent coin. But now the smallest that you see is the goldenish 5 cent coin, right? Yeah. So last time we could pay with the 1 cent lah, because things were cheaper. Before inflation came in, you know, then everything become more expensive. Maybe next time we will not see 5 cent anymore already. Right, so next. I think we'll end at the next question. Inequalities. So solve the inequalities. 2x less than negative 31 minus x. Bring all the x to one side. And when I say that, bring all the x to one side, I mean I only want to see x on one side. And we do so by adding x to both sides. Because originally on the right hand side we had a negative x. So to get rid of that, we need to add x. Plus x to both sides, okay? So plus x to both sides, 3x is less than negative 31. So you treat it like you treat your solving of inequalities like your solving of equations. It's the same, except when you multiply or divide by negative number, then the sign change. Otherwise, everything is the same. Okay, so you divide, so you get x less than negative 31 over 3. And that is the solution. If they say represent, they didn't, but if they say represent your answer on the number line, so you draw a number line, x, identify where is negative 31 over 3. So since that is the only answer, that is the only number, you just have that, is good enough. It is a hollow circle because there is no equal sign. Don't have. So it is a hollow circle. If there is a less than or equal to, then you must color the circle. And x is less than that, so put it to the left. Oops. Put it to the left. This is representing on the number line. Okay, so now in part B, 1 over 7x is less than or equal to negative 10 over 21. So all you need to do is just multiply by 7 on both sides. You get x is less than negative 10 over, less than or equal to negative 10 over 3. So in the second number line, if they ask for it, negative 10 over 3, okay, so color it because there is less than or equal to, then draw arrow to the right hand side. Alright, so that is our lesson for today.